Hubble diagram is probably the most traditional of cosmological tests. It plots relative luminosity distance of sources as a function of their redshift. And early on, the brightest things that astronomers could think of to look at were the brightest cluster galaxies. They can be detected out to redshift of a few tenths from using the technology available at the time. That turned out not to be quite far enough to really sense cosmological effects. But moreover, the problem was that galaxies being made out of stars evolved because stars evolve. And moreover, they merge, so their total stellar mass increases. And so by the 1980s, it became clear that Hubble diagram for galaxies is basically an impossible task, because the evolutionary effects really dominate over any cosmological effects. The difference between different evolutionary models is much larger than between any plausible range of cosmological models. Supernovae were also suggested as standard candles as early as the 1960s by Zwicky and his collaborators, but back then nobody knew how to make them standard enough for this purpose. The revival of this test came in mid-1990s, where astronomers learned how to standardize brightness of supernovae in the ways that we covered earlier in the class. And because they can be seen further away, our telescopes are bigger and detectors are better, suddenly they became a viable cosmological test again. Do note that some uncertainties still remain about the origin of supernovae type 1a and exactly what happens in those explosions, but astronomers try to come up with tests to control possible systematics. We do see some variation in their light curves, but most of that can be indeed taken out through standardization procedures. There's some remaining questions, such as whether there is an additional parameter, there is an evolution, and there are hints that indeed such things do happen, but at such a subtle level they do not affect the cosmological results. Still, keep in mind, these are messy stellar explosions which we can barely model in computers today, and the more realistic models we get, the more complicated they look. So it's still possible that some additional uncertainties may be present using supernovae as standard candle. These are examples of images of some of the very distant supernovae taken with Hubble Space Telescope. This is just to indicate how difficult these observations are. Not only do these faint supernovae have to be discovered, they have to be discovered early. Their light curves mapped, their redshifts obtained, all of the different corrections applied, and only then they can be used in a Hubble diagram. All this requires a lot of effort by the best people and best equipment we have. Anyway, that was done in mid-90s by two groups working independently. One was the Supernova Cosmology Project at Lawrence Berkeley Lab, led by Sol Perlmutter, and the other one was High Redshift Supernova team, led by Brian Schmidt and Adam Rees. The two groups essentially produced the same result at roughly the same time, and more or less independently. They both found out that the high redshift supernova Hubble diagram requires introduction of the cosmological constant or vacuum energy density in order to fit the data. Whereas there was a lot of circumstantial evidence for cosmological constant prior to that, this was the first time that majority of physicists really started paying attention and taking this possibility seriously. Here we see Hubble diagrams with the main trend lines subtracted, a particular model subtracted, and then residuals fit through a variety of other models. The model that fits the data best is the one that includes cosmological constant at the level of approximately 70% of the critical density. This was a spectacular result, and the three leaders of the groups deservedly got Nobel Prize for that work, although, again, it's important to point out that these are large team efforts and not necessarily reducible to a handful of individuals. This is how science today operates. Here is the Hubble diagram replotted now in the original traditional sense of scale factor versus time. And so the points extend to the past. You can see that they select a particular curve, and that curve corresponds to cosmological constant driven universe that expands forever. Many other groups have undertaken this work since then, and they all pretty much agree. The results just get better and better. Here is an example of one of the more modern high-redshift supernova Hubble diagrams, and colors of points correspond to those from different groups. As you can see, there is an excellent mutual agreement, and the signal to noise is really getting to be very good. So this was the upshot of the supernova Hubble diagram. On the plot of critical density, on the plot of density parameters, matter on the x-axis and vacuum, or cosmological constant, on the y-axis, the measurements define an error ellipse, which is tilted, and the flat universe corresponds to a diagonal straight line as shown here. They do intersect, and intersect roughly at density of the matter of 0.3 of critical density and density of vacuum about 0.7 of the critical density. So this was the first time that it was possible to say that if the universe is flat, then there must be a cosmological constant. But note that these error ellipses are pretty large, and they do not really nail down the exact cosmological model. The zero value of cosmological constant is sufficiently far from the best fit that it can be excluded. But exactly what mixture of vacuum density and matter density is at play had to be determined using some other method. An interesting twist to this is to use cosmic gamma ray bursts as alternative standard candles. These are even more spectacular explosions, but it turns out that their gamma ray luminosity can be also standardized to a nearly constant value using a variety of other parameters. At any rate, it's an independent test on what supernova results are, and here are the error contours from gamma ray bursts alone. They're bigger than those from supernovae because gamma ray bursts are not quite as good standard candles, but they produce more or less the same result. Now, a few words about the other classical cosmological test, the angular diameter test. Here we compare relative angular diameter distances to sources at different redshifts. And in the past, things like isophotal sizes of giant elliptical galaxies, mean separation of galaxies in clusters, or separation of radial lobes in radio sources were all suggested as standard rulers, and none of them really is, for the same reasons as before evolution. Here are some of the early results trying to do that. And interestingly enough, all of these have also been consistent with what we now know is the correct cosmology, but people simply could not be sure because of the evolutionary effects that were not well understood at the time. This test got revived through the cosmic microwave background, and it's probably now the most important of all of our tools. So next time we will talk about cosmology using cosmic microwave background fluctuations, what really led us into the era of precision cosmology.